In the earlier lecture, we had discussed about reasoning with uncertainty, and there we discussed about certainty factor algebra, and we also had shown that how Mycin uses certainty factors in order to deal with uncertain reasoning. A very powerful tool for reasoning with uncertainty is probability theory and probabilistic techniques. That is also known in another term, that is called statistical reasoning. Many of you might be familiar with probability, and we will have a brief recapitulation of the basics of probability theory today, and then from there we will proceed towards reasoning using probabilities of events. Just to give you an idea, you have seen in the earlier lecture that we are having some confidence associated with some rules. However, these confidences or the certainty factors or the measure of beliefs or disbeliefs were being attributed by subjective decisions taken by the experts. However, if we had actually conducted a number of experiments, say a particular rule A implies B, out of 1000 times when A is true, how many times did B become true? If we could make a thorough experiment about this, and based on the frequency of the times when A implies B really holds, we could have really given a much more realistic factor, realistic value, a realistic, more realistic strength of belief to the rule. So, that is the basic idea of probability theory, probabilistic reasoning. However, there are associated problems and complications as well. However, before going towards the probabilistic reasoning, we will be discussing today about probability and uncertainty, but before going into that, we will have a relook on the issue of uncertainty in decision making proper. You can see that uncertainty, in the earlier lecture we had talked about different types of different sources of uncertainty. We are looking at the same issues, but being presented in a different way. One issue is expressiveness. We have to deal with uncertain situations because of our inherent limitation of expressing very concretely some of the facts that we deal with. So, the question is, can concepts used by humans be represented adequately? Can the confidence of the experts in their decisions be expressed? The experts take some actions. When they are faced with a situation, they apply their intuition, their common sense, their experience, and take some actions. But what really led them to take that action is often not very clearly expressed. If you recall, while discussing about knowledge acquisition, we had mentioned the same thing, that is very difficult to really extract the expertise from the experts. Now, when the experts take a decision under an uncertain situation, how do we ensure to extract the exact mechanism or confidence or the probability, whatever, what the expert applied? The second issue is comprehensibility. How do we represent the uncertainty? first of all, that uncertainty has to be represented, and secondly, we have to, that representation must be such that we will be able to utilize that in the standard reasoning method, like modus ponens or rule based inferencing or whatever. If you recall, we will not call an organization of information to be knowledge unless that is usable to perform inferencing. The same is true here. We have to represent uncertainty in a way which can be reasoned with. The third factor is correctness. How correct is it? Okay. When we take probabilities, obviously, anything that is having a probability of 0.7 is not known with certainty. So, if I take this 0.7 probability as a measure or as a key factor to take any decision, how correct would my decision be? A probability of 0.7 means that 70%, in 70% of the cases it is true, but in 30% of the cases it is not. So, obviously, there is a chance that the decision that I take will not be correct if it falls in that 30%. Therefore, the probability must be very reliably calculated and gathered from a huge set of data. The other thing is relevance ranking and long inference chains. We have seen in the earlier lecture, in our earlier discussion about certainty factors, that as we propagate through rule chaining, for example, A implies B, B implies C. As we propagate or proceed through a longer chain, and when our starting point A is known with some uncertainty, not, that means not 100% certain, and A implies B is also an uncertain rule, then obviously B is inferred with a lesser certainty. So, some error that may have gotten when I have assigned that uncertainty in the rule or in the fact A will propagate in B, and then when I use the rule B implies C and take a uncertain decision about C with some belief, then if there were some error, that error will be propagated. So, that is another issue. Another important thing is the computational complexity. We may like to represent uncertainty in different ways, but ultimately we will have to be able to compute with that, we will have to, the computer will have to take the decisions. So, the computational complexity, that is whether it is of the order n, n square, whether it is polynomial or whether it is exponential, all those issues will come up because we have to take the decision in some time. In some cases we have to take it in real time, but in some other cases also there must be a finite time. We cannot spend a lot of time, huge time to just make a computation for one uncertainty handling, and there will be so many other uncertain cases, and for every time we will not be able to devote that much computational time. So, computational complexity becomes an issue because we want to have fast decision making. The other source of uncertainty is data, missing data. Some data may not be at all available. That is, suppose we have got sensors put in different places, but there are some very difficult places where it is very difficult to approach and put in a sensor. So, we will not get some data from there. There may be that we are collecting data from 100 sensors, but some of the sensors failed and we are not getting data. So, but in the absence of that data also we will have to carry on the reasoning, that is missing data. The other thing is unreliable data. The data may be unreliable because when we receive the data, that data is propagated through some channel and that channel may be noisy For example, you are carrying out a blood test and the machine of the blood, whatever machine you are using for the blood test is not very reliable. So, you get a gross idea of the blood report, but that is unreliable. In some cases it is ambiguous, all right, and imprecise. We do not very clearly specify those. We will see these examples of ambiguity and impreciseness later. We have already seen some expressions like very tall, quite big, sometimes, frequently, seldom. These are some of the statements that we make which are not precise. Seldom, often, how many times in a day, how many times in a week. Sometimes the data may be inconsistent. You may get the data or the information from multiple sources and the data may be inconsistent. Sometimes the data may be subjective and sometimes the data may be derived from defaults. Now, this requires a special mention. What do we mean by default? Default means assuming something when nothing is known to the contrary. So, this is if you recall, in the passing we had said I had mentioned about abductive reasoning, deductive reasoning has been discussed. We have also mentioned about abductive reasoning. There is another very interesting type of reasoning called default reasoning. Now, what does this default mean? Default means, say, assume something x to be true when nothing is known to the contrary. All right. That means, I do not know, I do not have any evidence, no evidence is right now available, that contradicts x, that says not x. There is nothing such. Okay. So, when nothing is known to the contrary, then assume something, that is called default reasoning. Let me give an example. Say, Fido is a dog, and you know dogs have 4 legs, all right. Therefore, I can infer that Fido has 4 legs. Now, if I know that Fido met with an accident and had one leg amputated, then obviously this reasoning will fail. Now, I am feeling tempted to ask you, what is this sort of reasoning? Fido is a dog, so I can say dog Fido, and dog x implies 4 legs x. From there I infer 4 legs Fido. What is this form of reasoning? I am sure you will be able to identify that this is our old friend modus ponens, which looks like P implies Q and P is true. So, we assume Q is true. Now, if I had known that Fido met with an accident and had one leg amputated, then obviously this would have failed. But in the absence of that knowledge, I will certainly apply this rule and assume that Fido has 4 legs. Now, say I have got some facts from the domain of cricket matches. Okay. So, say I want to know that say batsman X I have got some details about batsman X. Okay. I know average runs scored by him, that is known by me, average runs scored by him, number of centuries he made, etc. Suppose in my knowledge base I do not know whether he is a right handed batsman or a left handed batsman. It is not known, nothing is there. Now, all of a sudden a query comes, which hand does X use while batting? Now, normally given these facts, I will not be able to answer this question because I do not have that information. However, if my reasoning mechanism says that for any such query, if nothing is known, if not known, assume right handed, then with this power I will be able to answer this question and I will say right handed X. However, this may not be true, but this is the default reasoning that we do, because might be now if here it is said left handed X, then obviously this information which is present will override this default, and this information will not be holding any longer. This is what is known as default reasoning. Okay. So, that is, so whenever we take some conclusion that is based on default reasoning, obviously there is some amount of uncertainty mixed in that. The second point that we are coming to is expert knowledge. As we are mentioning time and again, that there may be an inconsistency between different experts, and so often the experts talk about plausibility, that is a best guess of experts, best guess. So, it is again not a certainty. The other factor that is important is the quality, the causal knowledge. If we know the causality, the cause effect relationship, in the last lecture I briefly touched upon that if I know that say the resistance of an electric circuit affects the current that is flowing, and also the voltage causes the current to flow. Now, this is the cause, this is the effect, and if we really know, for example, this causality is known by this part, is known by the well known law of physics, Ohm's law. That is known, we have got a deep understanding of the causality, the relationship between the cause and the effect. But in many cases that is not true. We do not know the area to such depths. For example, psychology. We are still trying to model the human brain. We do not have any clear grasp on how the mind or how the psychology works. So, we will have to, we cannot make a very strong causal commitment over there. Instead, in those cases, in many cases where the causal knowledge or the deep understanding is not available, we go through statistical associations, which are observations. So, we look at several cases and based on that we carry on our decisions. Okay. Knowledge representation, that is another point. How do we represent knowledge? That is another issue. When we represent knowledge, we have already said while talking about knowledge based systems that we cannot really make a complete knowledge base. So, there will be some sort of, in order to make it really good, we have to narrow down the domain so that we can go deep into it. So, we actually work with a restricted model of the real system. The actual system may be very diverse, but we are working with a restricted narrow version of that and limited expressiveness of the representation mechanism. Now, also inference process, that is another important issue. We know what is deductive reasoning, deduction. We know that that is sound. So, the derived result is formally correct, but we may find that it is wrong in the real system. Why? Because the rule may itself be wrong. There is a subtle difference. My reasoning is right, but my rule is wrong. So, again coming back to our modus ponens, say P implies Q and and P, I infer Q. This inference process is fine. This inference rule is okay, is correct, but the correctness of this result depends on the correctness of this rule. If this rule is not correct, then obviously this inference will also not be correct. So, there is a difference between the soundness of the inference process and the correctness of the result. Even if the inference process is sound, the result may not be correct unless the axiom or the theorem or the rule that I have written over here is not correct. Okay. Inductive reasoning. Now, this gives me an opportunity to introduce inductive reasoning methods, and the new conclusions that we get are always not well founded. Earlier, again, the different inference mechanisms with which we are by now familiar is deductive, the other one is abductive. Now, I introduce another one, that is inductive reasoning. And actually it is not new, because you will see that day to day we often use this. Say to a child, I show a ball, I show one ball, all right, a particular ball that is round shaped object, all right. Say A1 is some round shaped object. and I tell the boy, the child, that it is a ball. So, the child associates the round shaped object with ball. Next, I show him another ball, okay, which is another round shaped object of a different color, and I say this is a ball. I show him another, might be a football, which is these two were smaller balls like cricket ball, hockey ball, etc. Now, I show him a football which is also a round shaped object, but the size is different. I say this is a ball. In this way I go on. Gradually, the child learns that for any round object that is shown to him is a ball. Okay. So, in this way, from these instances, all these are instances, and based on that the child learns a rule that is for all A that is round, okay, for all round objects, all right, AI implies ball. Okay. Now, I show him an apple or an orange which is round, well shaped orange, and the child will infer it as a ball, because he has inferred that all the round shaped objects are balls. Why? Because I have shown him n number of, large number of instances, n number of instances, and from there I have made a generalization. Now, if these instances are proper, then for most practical purposes this will be a very useful way of reasoning. All right. How do we infer? How do we learn? Actually, most of the things we do is through induction. This is the process that goes on. So, this is known as inductive reasoning. However, as we have shown here, this is not sound, because there may be counter examples. All right. The same unsoundness was there in the case of abductive reasoning also. So, inductive reasoning, in that the new conclusions that we arrive at are not always well founded. Okay. The other thing is individual rules. There can be errors in the individual rules, there can be representation errors, inappropriate application of the rules. Now, we have already seen this case, that the likelihood association of the evidence, we have seen, just as we did in the case of certainty factors, we had put in several certainty factors with a premise for the conclusion and the combination of evidence from multiple premises. All these examples we have already seen while discussing about certainty factors. In rule based system, there can be another issue, like uncertainty can come up when we have got multiple paths and there are multiple rules to use. So, conflict resolution, you remember that conflict resolution means from the set of multiple rules we select one or two and apply them. Now, which one is selected? That may give rise to some sort of uncertainty. The compatibility, the contradiction between rules, the subsumption, one rule may be more general version than another one, there may be missing rules. When we collect the data from multiple sources of different reliability, we will get again a varied, the reliability of the ultimate fused data set will not be the same. Now, in order to handle such complicated scenario, now we will move to the probabilistic approach, and first we will start with the basics of probability theory. I assume that most of you know about the basics of probability theory, but there is no harm in recapitulating it once again. Probability theory is a mathematical approach for processing uncertain information, and we talk about a sample space. What is a sample space? The set of all possible events. For example, when we deal with a die, when we toss a die which has got 6 faces, the possible outcomes are 1, 2, 3, 4, 5, 6. So, that is a set. It can be discrete or continuous. For example, when I think of the possible temperatures that can be there tomorrow, the typical weather report, what will be the maximum temperature? It can vary from in a continuous range. So, this sample space can be considered as a set. And what is a probability? Probability is a number, real number, p x I. X I represents any of these events. So, we call these to be the events, and any of these events is associated with a number, real number, which denotes the likelihood of the event to occur. And as you know, it is a non-negative value between 0 and 1, and total probability of the sample space is 1. That is the basics. And just to give the example, again we can always think it as a set, the set of possible events in the case of a dice throwing. The possible events are 1, 2, 3, 4, 5, 6. So, when I throw a die, any of these discrete events will occur, either 4 will occur or 5 will occur, and each of them have got a probability associated with it. And if the dice is fair, then you know that the probability of an event, so this is x I. So, probability of x I is 1 by 6 in this case, because all of them are having equal probability. Fine. And the total probability of the sample space is 1. When all these are added together, that will be 1. Now, for mutually exclusive events, what is meant by mutually exclusive events? That two events cannot take place together. When I throw a coin, it cannot be head and tail, it will be either head or tail. The probability of at least one of them is the sum of their individual probabilities. Now, the probabilities can be of two types, experimental probability or subjective probability. Experimental probability is based on the frequency of events. Say if I carry out a fair experiment of say the throwing the die, or if I take a biased coin, if I throw it 10 times, maybe it will not be 5 times head and 5 times tail. If it is biased, then maybe I will get 7 times head and 3 times tail, but with that experiment being done quite a number of times, we can come to a fair degree of association of the frequency of the events. The other thing is the subjective probability, where, as we have seen earlier, that is based on the expert's assessment of the whole thing. The next thing is compound probability. In the last lecture, we tried to explain the idea of independent events. Suppose there are two sets. Here the possible outcomes are, say 1, 2, 3, that is my space x, and there is another space y. Say when I press the bell 1, these are, say, there is a sort of a button, or I press, I can press any one of them. Somebody is asked and he will press this, and here there are some other events, say A, B, C, that will appear as I press a button. Now, if there be a direct association that if 1 is pressed, then A will be displayed, when 2 is pressed, B will be displayed, then there is a direct causal relationship between these two and they are not independent. On the other hand, if it be the case that both the appearance of 1, 2 or 3 or A, B, C are absolutely random based on their own probabilities. So, there are some probabilities of P A maybe say 0.6, that most of the time A occurs, P B is 0.3 and P C is 0.1, all these are adding up to 1 for this space. Most of the times probably I will get A irrespective of whether I press 1, 2 or 3, right. So, in that case the appearance of the pressing of the button 1, 2 or 3 and the appearance of the symbols A, B, C are absolutely independent. There is no causality among them. Okay. In such cases, the probabilities do not affect each other in any way. Now, the joint probability of two independent events A and B is given by P probability of A and B, that is the number of intersections A and B divided by the total number of elements in the set, and that can be computed as the probability of A times probability of B. For example, if I again thinking of this same example 1, 2, 3 and A, B, C, this is the display, what will be displayed, and this is the key that will be pressed. Now, I can compute the number of times that 1 has been pressed and A has appeared. Now, if this be random, it has got its own probability. Say here we said that P of A was 0.6, P of B was 0.3 and P of C was 0.1, and similarly say here we have said P of 1 is 0.6, P of 2 is 0.2 and P of press 3 being pressed is also 0.2, because that should also add up to 1. Then the joint probability of that 1 will be pressed and A will appear will be probability of 1 multiplied by probability of A occurring, that will be equal to 0.6 times 0.6 equal to 0.36. Now, this will hold only if this and this are independent. They are absolutely independent. This is coming from one set and this is coming from an independent set. So, that is known as the joint probability or compound probability. Similarly, A or B, that is the union probability of two independent events will be P A plus P B, the probability of A plus probability of B minus the joint probability when they are occurring together. All right. This is also very simple to understand. Quickly, if we go back to the earlier example, say we know they have got their probability 1, 2 and 3. I am saying now what is the probability that 1 will be pressed or A will appear. Obviously, 1 will be pressed has got the probability to be 0.6 as we had done earlier. The fact that A will appear also has got a probability 0.6, but there is a joint probability in that I am already considering the cases where 1 and A have jointly occurred. So, that was 0.36. So, minus 0.36. So, that one will come to 1.2 minus 0.36, whatever that comes to, that will be the union of these probabilities. Okay. Next, so the basic axioms of probability we can quickly summarize that probability is a value between 0 and 1. P E denotes the probability of the event E. If the event E is always true, then P true is 1, that is a certain event. There is no uncertainty involved in it. Similarly, P false is 0, that is it is an impossible event. Okay. P A, there is a probability of A occurring is equal to 1 minus probability of not A occurring. All right. That since the total space is 1, then obviously the probability of A occurring must be 1 minus this. Similarly, for those of you who are not sure, again this example will tell you 1, 2, 3 and P A is 0.6, P B is 0.2, P C is 0.2. So, what is the probability of not A? Probability of all these together is 1. So, probability of not A means the probability these two cases occurring, A is not occurring, I am sorry, I am sorry, this is A, this is B, this is C. So, probability of not A is either probability of B or probability of C. So, that will be the union of this. So, it is 1 minus the probability of A, that is basically if you look at the probability of B in this case and the probability of C taken together. So, it will be 1 minus 0.6 equal to 0.4. All right. Similarly, this one we have already discussed. So, these are the basic P A or B we have already discussed. So, these are the basic axioms of probability which we will need to use. Next, we are coming to relatively, now till now we are discussing about independent events. Now, we are coming to the case of dependent events. Now, dependent events means they affect in some way. One of the ways they can affect is the causality. If the voltage across a circuit is increased, the current flow will increase. There are other ways also in which our reasoning can affect. For example, if there is a murder, then there will be some blood stains. So, if we see blood stains, from there we can also reason back towards murder. Okay. So, evidences also sometimes help in reasoning, and that is very useful in the case of diagnosis when we look at some fault and try to reason back to the cause of the fault. Now, if two events are dependent, then that is the fact that one event has occurred will certainly influence the occurrence of another event. This is known as conditional probability, that is conditional probability of an event A given that event B has already occurred, that is given by P A given B. Now, here you will again find some similarity with our certainty factor case, where we are time and again writing M B H given E. Similarly, here we are saying probability of an event A occurring if B has occurred. What is the probability of this? Now, B has occurred or B has got a particular probability of occurrence. Okay. In that case, what is the probability of A's occurring? That is known as conditional probability. Okay. And that is given by P, A and B, that is A has occurred and B has occurred, divided by probability of B. All right. Now, there are two types of probabilities. So, in the earlier case also you can think of now what is this is now here you see that the probability of A and B occurring divided by the probability of B. Now, the probability of B is known a priori. So, here we have to talk about two types of probabilities. One is a priori probability, that is the probability of a priori, that is and we also write it as a priori, that is known beforehand. Probability of B we have computed irrespective of A. Irrespective of A, I have computed the probability of B through experiment, and suppose I have found that in general B occurs with a frequency of 0.6. You go to a village and carry on some experiments just on the occurrence of malaria in that village. Okay. So, P of malaria, you find that every 6 out of every 10 persons, 6 persons are inflicted with malaria. So, the probability of malaria is 0.6. All right. Now, we would like to see probability of say fever. This may not be a very good example. When they had malaria, when they had malaria, what is the probability of fever? How many of these people had fever? Assume that all malaria cases are not resulting in, are not giving rise to fever. Let us assume that. So, in that case, what we are trying to say, it is the probability that somebody will have fever somebody will have fever, he has fever and malaria, and I find that the probability of that he had fever and malaria, on those cases I find it is 0.9 say. All right. Now, out of these, malaria has got an independent probability, a priori probability, that every 6 people will have malaria. So, they got a malaria, they got the fever because of the malaria. Should people can have fever for some other reason also. So, we compute this by dividing with the a priori probability of malaria. So, that is because they are not independent, I divide it with 0.6, and whatever value comes up, that is my conditional probability of fever given malaria. All right. So, that is conditional probability. So, next I just now mentioned about a priori probability. So, this is the thing that we are going to say about it, that prior probabilities of events A and B, suppose we know, is P A and P B. We know the prior probabilities. We know the prior probabilities of P A and P B, but if we know A for sure, then probability of B might change. Okay. If we know A for sure, then this is represented as the conditional probability of B given A. Now, let us go back to that earlier said that doorbell problem. Doorbell rings at midnight, that is D. W is Mohan wakes up at midnight, and suppose the a priori probability of the doorbell ringing at midnight is 0.001, that is the probability is really less. and Mohan's waking up at midnight for different reasons, doorbell or for some other reason, okay, feeling very hot or uncomfortable, whatever, is 0.01. And we say that the probability of this Mohan's waking up with doorbell, when the doorbell rings, is 0.8. Now, this is a conditional probability. These are a priori probabilities, that doorbell or no doorbell, the probability of Mohan's waking up is 0.01. For any reason, the probability, a priori probability of the doorbell ringing is 0.001. And this is a conditional probability, that if the doorbell rings, then Mohan will wake up, that is 0.8. So, that is there is a difference between the types of probabilities. Now, in order to handle this sort of cases, there is a very interesting and famous rule that is known as Bayes' rule, that is used for computing the conditional probabilities. Probability of an event A given B, that is, if B is known, what is the probability of A, can be computed as by this formula. See, here we are trying to find out what is this? This is a conditional probability. Conditional of what? Probability of A occurring when B is known. Now, if we know a priori probability, the reverse relationship, I know the a priori probability of A, I know the a priori probability of B, and I also know the a priori probability of B occurring when A occurs. You see, what we are trying to do is a cause effect relationship. Then this is the formula that gives me P A given B, that can be derived with P B given A multiplied by the a priori probability of A divided by the a priori probability of B. Now, this can be easily derived like this: P of A and B, as we know, is what is this? Is P A given B times P B, and again P A and B is P B A multiplied by P A. All right. If I just change it now, from this I can say P, this one is P A and B divided by P B, and P A and B is P B A divided by P A times P A. So, what is the implication of this? Before going to the implication of this, let us look at this example. Say this was from the earlier example, that a priori probability of doorbell ringing is 0.001, a priori probability of Mohan's waking up is 0.01, a priori probability we know that if the doorbell rings, Mohan will wake up is 0.8. Then what is the probability that when Mohan woke up, he woke up because the doorbell rang? I want to find the reverse thing. Then by Bayes' rule, we will simply use this P W D, this one, multiplied by the a priori probability of this denominator, okay, the event. This is the event, this is the hypothesis, the event that is 001 divided by the probability of a priori probability of waking up, because I have to divide by this, because anyway that would have happened. So, I get a normalized probability of P D W is 0.08. Now, this is a very important technique, and it has got far reaching implication. Just before concluding this lecture, I will try to say what it really implied, and this will form the basis of the next lecture also. We are given some event, and from there we try to come at a hypothesis, and I really want to find out what is the probability of that this hypothesis is true given this event. Say this event is fever, and probably this is making more sense now. If he has fever, he had malaria. what is the probability that if he has fever he will have malaria? I want to find that out, that fever is implying malaria. I want to find out the probability of this. Now, I know P of E given H. What does it mean? This means what is the probability that somebody who has malaria, somebody who had malaria had fever also. Say how many times it happened? I find that this probability is something like 0.4. So, I know this a priori. So, I know this thing a priori, and I also know the probability of fever in a particular locality. I also know the probability of malaria in a particular locality. These are the a priori probabilities. So, using this one and this one, I am trying to find out this. Okay. So, I know these a priori probabilities, and I also know that if somebody has malaria, then he has fever. This part is known. So, from there, from the knowledge of this, I am trying to derive this, and that is being done using, that is exactly what is being done in the case of Bayes' theorem. And this conditional probability is very important for our purpose, for the simple reason, as you will realize, that it is a way of dealing with these rules, that E implies H. This is nothing but a rule, and I will have to reason through these implications, and if I know the probability of this, then I will be able to say, if I know the probability of this, then it will be a much stronger measure than what we had in the case of certainty factors, which was a rather a subjective measure, right. So, Bayes' theorem forms a basis of reasoning, probabilistic reasoning. In this lecture, we could not complete that, but in the next lecture, we will start with the Bayesian reasoning techniques using this Bayes' theorem. And one very popular tool and powerful tool that has been designed for reasoning in the probabilistic domain is the belief network, which we will be discussing in the next class, next lecture, but this forms the basis of the basic probability theory requirements that will be the main thing is the conditional, the idea about the conditional probability and the Bayes' theorem. Thank you.